class. So today we will talk about, or we will learn about something which is known as compensation. Okay. So what is basically compensation? So as the name suggests, that obviously we are trying to compensate for some shortcomings, right? So the basic function of a control system is that you can say that the primary purpose of a control system is that it is designed in such a way that it can perform, or it has to perform some specific tasks. So the specific task, the performance can be specified in terms of, like, let's say, the accuracy of the system, the relative stability of the overall closed loop system, then the speed of the response. So all these are different performance specifications which need to be met in the output of a closed loop control system, right? So we have to design the control system in such a way. So the parts of the control system is that it has so previously we have seen that it has a plant. So plant is something which is the actual the main system which we are trying to control. Then we have we have a controller in cascade, that is in the forward path with the plant. Then we can have a feedback loop which is in form of a negative feedback or a positive feedback, in generally negative feedback, because that is where the stability of the system improves. Then, so these three are till now we have seen that these three are the basic components, you can say, of a control system, right? So whenever we try to design the control system, so the specifications which are mentioned, which are given to, let's say I am a control designer, and I have a plant, and I have to design the control system in such a way that, let's say, A, B, C, D, four or five performance specifications are given. Okay, so I have to modify the controller, I have to tune the controller, I have to change the feedback in the feedback sensor or the feedback transfer function, such that those given conditions are met. Okay, so now these performance specifications, they should not be from the design point of view, this performance specifications, we should not make it very stringent. Okay, so what do we mean by it should not be very stringent than what is necessary? Let's say that since we have both the time domain and the frequency domain, we can do the analysis in both the time domain and the frequency domain. So let us say that the steady state operation of the closed loop system, that is of primary importance to me. In that case, we should not unnecessarily complicate the system or unnecessarily complicate the control system design in such a way that it has a very good transient performance also. Maybe we are not interested in the transient performance. In order to have a good transient performance, we need to modify the controller and the feedback sensor in a different way. Okay, so depending on what my performance specification is given, or which performance is of actual importance to me, depending on that, we would like to keep the control system design as simple as possible. Otherwise, obviously, if I want to have an if I want to meet an ideal set of performance specification, that is, it has to have a very good transient response, that is, the speed of the response should be fast, it should be very stable, the accuracy also should be very high. So if I have to satisfy all these performance specifications, then obviously the system will become much more complicated, right? So what we do is that depending on what kind of depending on which type of the or what part of the output is of more importance to me, depending on that, we will focus on designing the control system. Okay, so till now we have seen that the three, so the plant, obviously you can't control the plant is given, it is sort of a black box to you. So you have to design the controller, you have to design the feedback sensor in order to control the plant, right? So you have to so here you have two parameters, or rather not two parameters, you have two blocks which can be modified, or which can, the parameters of which can be modified in order to get the final desired response. Okay, so another thing that we can use is known as a system compensation. Okay, so the first line of you can say, the moment you have a plant is given to you and a set of specifications is provided to you, so the first line of action for obtaining that desired output is that we will first of all adjust the gain of the system, right? So that would be the first step to achieve a satisfactory performance. But So that adjustment of the gain of the overall system, that is usually done by something which is known as system compensation. Okay, so we use this compensation, either you can use it in the forward path, that is in cascade with the plant and the controller, or you can use this compensation in the feedback path also. Okay, so in that case it will be known as a feedback compensation. But as you know that if the moment we increase the gain of the system, even though that gives you a good, that improves the steady state response, but that improvement is obtained at a cost of the reduced stability. So that means that whenever the gain of the system that is increased, the relative stability of the system becomes poorer. Okay, so we have to do a trade-off, and then accordingly we have to use a proper controller and a proper compensation for the system. So the basic definition of compensation is that we have to redesign the system in order to incorporate additional elements, and that incorporation of those additional elements, they will alter the overall behavior or the overall output that is being generated from the system. Right. So here in this figure, you see that, so this is a compensator we have added. So this is basically a closed loop system, a negative feedback closed loop system. So we have added a compensator before the plant. So you can also have a controller before in between the compensator as well as the plant also. Okay. So as I have already told that there can be two types of compensation. So one is cascade compensation, where the compensator is placed in the forward path, and the other one is the feedback compensator, where in the feedback compensator, in the feedback compensation, this compensator is placed in the feedback loop, in the negative feedback loop with the given plant. Okay, so these are the two types of compensations which are generally used in order to meet specific criteria that is given for the system. Now, if a plant and a given set of specifications is provided to you, so the main task is that you have to design a suitable compensator so that the overall system will meet the given specifications. Now, this choice of this desired system performance that can be specified in terms of the transient response characteristics or in terms of the steady state response. Okay. So this desired, so you can say that this desired performance specifications in terms of either the transient response measures or in terms of, so either in terms of transient response measures or in terms of the steady state response or the steady state error, you can say, the overall accuracy of the system. Okay, now the steady state error, generally these are specified in terms of the error constants, the static error constants which we have talked about. So error constants, so the value of these error constants, that is Kp, Kv and Ka, these error constants, they define the steady state error of a particular system for a specific set of input. Okay, and for the transient response measures are that in terms of the relative stability. So these are in terms of the relative stability of the closed loop system or the speed of the response. So these are generally the type of or the specifications which are generally provided to you in order to design a compensator. Okay. So in the time domain, basically this relative stability that is controlled, or this can be governed by manipulating the value of zeta, or in other terms you can even manipulate the value of the peak overshoot. Right, so these will give you, and the value of zeta and MP, that will indicate about the relative stability of the system. And for the speed of the response, so speed of the response, this is generally defined by the rise time, then the peak time, the settling time. All of these, they define the speed of the response. Similarly, if you go in the frequency domain, so these are for the time domain. So in case of frequency domain, this relative stability, this is done by, so let's say in frequency domain, if we do the frequency domain analysis, this relative stability can be defined in terms of this peak resonance or the phase margin. And the steady state response, this can be defined in terms of the resonant frequency or the bandwidth of the system. Okay, so now these compensators, basically they can be of different types. They can be electrical, they can be electronic, they can be mechanical, hydraulic, pneumatic. All variety of compensators are available depending on what type of system you have and what all are the specifications you need to meet. But in most of the cases, we usually use either an electrical compensator or a corresponding electronic realization of the compensator. Okay. So now this choice of whether, so since I have already told that you can either use the compensator in the series, that is in cascade, or in the feedback. So how do I choose that whether I have to use a series compensator or the feedback compensator? So this choice of the series or feedback compensation, that basically depends on the nature of the signals in the system, the power levels at various points. So obviously the power level at different signals at different points of your system, that will not be the same. So depending on what all are the power levels, then what all are the available components to you, then how much of the cost that you can accommodate for designing the overall system. So all these parameters, they govern or they indicate which sort of compensation would be suitable for your case. So either you will use a series compensator or a feedback compensator. In general, the design of a series compensation is much more simpler compared to a feedback compensation, because you can see that in case of a series compensation, you can just add the compensator in the forward path. But in case of a feedback compensator, it doesn't remain like a single loop system, it becomes multiple loop. So there is one loop with the compensator over here and the other loop with the actual feedback of the system. So it becomes a multi-loop system if you want to use the feedback compensation. So that means that the design of the cascade compensator is obviously much more simpler compared to the feedback compensation. But the problem with feedback is series compensation is that you need additional amplifiers in order to increase the gain or in order to provide isolation of the compensator from the other components. Okay. And the number of components which are required in the feedback compensation, that is usually less, since the energy transfer is happening from a higher power level to a lower power level. Now we'll talk. So this is the basic concept of compensation. Okay. Compensation that can happen there are three types of compensations, you can say. Okay, so the first type of compensation is a lead compensation. Then you can have a lag compensation and a combination, that is a lead lag compensation. Okay, so in case of a lead network, so if we have a lead compensator, so that means that if we provide a sinusoidal input to that network, the output of the steady state output of the system has a phase lead with respect to the sinusoidal input, then we say that system that is a lead compensator. So the output of the compensator that will have a leading phase angle with respect to the sinusoidal input. So then that network is known as a lead network. So similarly, a lag network, in case of a lag network, the output would have a phase lag with respect to the input. Right, and when you have a lead lag network, a combination of both lead and lag, so in that case both a leading phase as well as a lagging phase is obtained in the output, but the frequency range at which the leading phase and the lagging phase is actually occurring, that frequency range is different. In general, the phase lag in the low frequency range, we get the phase lag, and at the high frequency range we get the phase lead. Okay, so the main so now comes the thing that why do we require, or what is the need of the compensator? So basically, if there might be two different cases. Okay, so the first case is, let's say that since we have already told that compensator is basically the first line of defense, you can say, or the first line of action. Right. So if your system, let us say that system is the open loop system is an unstable system. Okay, so in that case, you need the compensator in order to stabilize the system as well as achieve some specified performance criteria, right? So if you have, let's say, if you have a type 2 system or a higher order type 2 or even higher order systems, so usually those type 2 or higher order systems, they are generally open loop unstable systems. Okay, so in that case, in order to make that open loop system into a stable system, so we use a lead compensator, and that Why we use a lead compensator? Because by using a lead compensator, you can increase the margin of the stability. Okay. Then the second case might be that the given plant, that plant is already stable, but it is not giving the actual performance which is desired, it is not giving the desired performance. So in that case, what we need to do is that we have to use a compensation in order to not to make the system more stable, but the main purpose in that case would be to achieve the desired performance or the performance specifications that are provided for the system. Okay. So generally, if you talk about type 0 or type 1 system, like lower order systems, they are generally generally open loop stable system. So in those kind of systems, so what we need to do is that we have to just modify the system in such a way that using the compensation, the overall transfer function of the system changes and the output is according to the desired output. Okay, so in that kind of a system, you can use any kind, like you can use a lead network, you can use a lag compensation, or even a lead lag compensation. Okay, but if your system is actually unstable and if you want to use a compensator in order to stabilize the system, then the only possible option is the lead network, because only in the lead compensator the margin of stability is improved. Now let's talk about like how this lead. So you can say that the main concern is the design of the compensator. So by using the compensator, what we are doing is that we are modifying the overall transfer function of the system, right? So modification of the overall transfer function of the system means that we are placing the poles and zeros of the compensator in such a way that the root locus or the frequency response of the overall system that changes, right? Since here we have, let us say that here, since we have a compensator, so this compensator will obviously have some pole zero configuration. So we are adding these pole zeros to the open loop transfer function, and by addition of these, what we are doing is that we are changing the addition of these poles and zeros. Obviously would affect the, if you draw the root locus will change, or if you want to draw the frequency response analysis like the Bode plot or the polar plot, everything will change depending on where you are placing the poles and zeros of this compensator. Okay, so depending on how this compensator is adding the poles and zeros to your system, the overall performance specifications will be, performance of the system will change, and we will try to make the performance as per the given criteria. This is the basic function, the basic circuit for a lead compensator. So basically, in case of a lead compensator has 1 0 and a pole. So the 0 is at a position of s equals to -1 by tau, and the pole is at a position of s equals to -1 by alpha tau. Okay. So if you draw that in this S plane, so you have the 0 over here. So this is -1 by tau, and you have a pole somewhere over here. Okay, and since the value of alpha is less than 1, so obviously 1 by alpha t, the magnitude of 1 by alpha t will be more. So you can see from here that in this kind of a pole zero configuration, the 0 is lying closer to the origin, right? So if you simply write the transfer function, so Gs will be equals to nothing but s plus 1 by tau divided by s plus 1 by alpha tau. Right, and that can be expressed like this, and where alpha is defined as Zc by Pc, where Zc is the 0 of the system and Pc is the pole of the compensator, right? And the value of alpha, and since the 0 is lying closer to the origin, so that means the magnitude of this 0 is lesser than that of the pole, so obviously the ratio will be less than 1, right? So the value of alpha is less than 1 and tau is greater than 0. Now, in order to realize this lead compensator using an electrical circuit, so you have to connect the resistance and capacitances in this way. Okay, so from here you can simply find out what would be the value of the E0 by EI, right? If this is the, so E0 by EI would be nothing but the overall transfer function of the system, right? So you can write, say E0 by EI will be equals to R2 divided by R2 plus this parallel combination, so R1 and in parallel to C, so R2 plus R1 by SC divided by R1 plus 1 by SC. If you just modify or do some simplifications or rearrangements, you will come up with something like this, and it can be expressed as s plus 1 by tau by s plus 1 by alpha tau, where tau is given by r1 into c, and alpha is equals to rt by r2 by r1 plus r2, and obviously the value of alpha is less than 1, right? So from here you can write that if you want to write it in the sinusoidal, so this is the sinusoidal transfer function. Right, so the sinusoidal transfer function would be, you will simply substitute the value of s by j omega. So you will get alpha j omega tau plus 1 divided by j omega alpha tau plus 1. So now here you see that this, in this case, and if I want to, okay, I'll come to that later on. So here you see that at 0 frequency, the network, it has a gain of alpha less than 1. So here you see that if the frequency is 0, so that means the magnitude of this GC will be equals to, so at omega equals to 0, so this magnitude of GC omega will be equals to alpha, and this value of alpha is less than 1, right? So in other terms, you can write that, so it has a gain of alpha, and the value of alpha is less than 1. Or in other terms, you can say that the gain of alpha is equivalent to an attenuation of 1 by alpha, right? Because since the value of alpha is less than 1. So in order to cancel out this DC attenuation, what you can do is that you can simply add an amplifier circuit in the subsequent stages. So that amplifier being 1 by alpha. So if you multiply these two, so then this value of alpha, it gets cancelled out, and you will end up with the value of GC of j omega will be only j omega tau plus 1 divided by j omega alpha tau plus 1. Okay, so you can say that you can visualize this lead compensator as a combination of this electrical circuit as well as a amplifier with a gain of 1 by alpha. So then for this combination, the sinusoidal transfer function becomes GC omega is GC of j omega will be equals to j omega tau plus 1 divided by j omega alpha tau plus 1. Now here you see that since the value of alpha is less than 1, so obviously the output, so this phase angle, so if you write the phase angle of this transfer function, so phase angle of GC of j omega, so that would be equals to nothing but tan inverse of omega tau minus tan inverse of alpha omega alpha tau, right? And this is basically an acute angle, a positive acute angle for alpha less than 1 greater than 0 for this case. So that means you can say that the output has a leading phase angle with respect to the input, and hence the name comes as the lead compensator. That is, that the output of this E0 will have a leading phase angle with respect to the input EI. Similarly, if you look at the electronic realization for the lead compensator, what we'll have is that we'll have an op-amp circuit which looks something like this. So if you simply derive the output by input relation for this circuit, so you will see that this E out by E in is nothing but Kc multiplied by s plus 1 by tau divided by s plus 1 by alpha tau. So this is the expression which we have got earlier. So this is s tau s plus 1 divided by alpha tau s plus 1. Right, so tau is plus 1 divided by alpha tau is plus 1, and there is some certain gain of the system. So for this system, for this kind of an electronic realization of the lead compensator, so the DC gain of the system is given by Kc into alpha, and the value of alpha is equals to R2C2 by R1C1, and Kc is given by R4C1 by R3C2. So you can simply do the calculation and we will see how these terms, if I assume that the value of alpha is given by these, Kc is given by this, then the DC gain of the overall system, that is equals to Kc into alpha, and this system will be a lead network if obviously if the value of alpha is less than 1. So value of alpha is less than 1 means R1C1 should be greater than R2C2, right? If that condition is satisfied, this network will act as a lead network, and if R1C1 is less than R2C2, in that case, the value of alpha is greater than 1. In that case, the same network, this will act as a lag compensator. Okay, so using the same configuration, just by simply changing the values of R1, C1, R2 and C2, you can switch from a lead compensator to a lag compensator. So now, as I have already told, that the phase lead of the compensator at a given frequency phi is given by tan inverse of omega tau minus tan inverse of alpha omega tau, right? So from here you can write tan of phi will be equals to omega, will be given by this term. So this term will have, so now we want to find out at what is the maximum phase lead which can be provided by this lead network. Okay, so the maximum phase lead will occur when d phi d omega is equals to 0. And for this condition to satisfy, this happens at a omega m of 1 by tau under root of alpha. So you can say this can also be written as under root of 1 by tau multiplied by 1 by alpha tau. So this is nothing but the geometric mean of the two corner frequencies. So since my expression is GCS is equals to 1 plus S tau divided by 1 plus S alpha tau. So that means that these two, so 1 by tau and 1 by alpha tau are the two corner frequencies of my system. So the geometric mean of the two corner frequencies, that is the frequency at which the maximum phase lead occurs. Okay. And the value of this maximum phase lead, that can be obtained just by simply substituting omega m in this expression. Okay. So you can say that tan of phi m is equals to 1 minus alpha by 2 under root of alpha. You can rearrange these expressions and you can find out the value of alpha in terms of sign of this maximum phase lead. Okay. Now similarly, if you see the polar plot of this transfer function, so this transfer function basically has this alpha term included in it. So that means that at omega equals to 0, the magnitude is equals to alpha, and at omega equals to infinity, this magnitude is equals to 1. Right, so that means the polar plot, it starts from this point, it moves and it goes over here. So this is, if you draw the polar plot for this transfer function, it will look something like this. Now if you have, so at this this omega m, that is at the frequency at which the maximum phase lead occurs, at that frequency the value of the magnitude of the compensator is given by 1 by under root of alpha. Now, if you want the phase lead which is greater than 60 dB, then it is always advisable to use, like, instead of using a single lead network with very small value of alpha, instead of that, it is always desirable that you use two cascaded lead networks, and so that both the lead networks, they have some moderate value of alpha. Okay, so that is sort of, you can say, that is a general practice. Okay. So now if we see the Bode diagram of this lead compensator, that is j omega tau plus 1 divided by j omega alpha tau plus 1. So here the Bode plot means, so here we have two corner frequencies, one is 1 by tau, other is 1 by alpha tau, right? So at 1 by tau we have, so if you draw the Bode plot, so asymptotic Bode plot will look like till omega equals to 1 by tau, it was at a 0 dB line. At omega equals to 1 by tau, you have a 0, so that means you will have a plus 20 dB per decade line. And it will keep on continuing till it hits the next corner frequency, which is 1 by alpha tau. At 1 by alpha tau, you have a pole. So that means there will be a minus 20 dB per decade. So the overall slope will become plus 20 dB minus 20 dB, which is equals to again 0 dB. So you will get a flat straight line like this. And the phase response will look like this. So now the disadvantage of the lead compensator, or the consideration that you need to, the important consideration here is that you have to choose the value of alpha depending on the inherent noise of the system. Okay, so generally the noise signals, the frequency of the noise signals, that is much higher compared to the control signal frequency. Now if you see the Bode plot, you see that at high frequencies we have the noise, and at high frequencies there is a gain amplification by a factor of 20 log 1 by alpha. And since the value of alpha is less than 1, so this gain is a positive, it is a gain which is greater. It is not an attenuation, but in other terms it is a gain. So you can say that in a lead compensator, the high frequency noise signals, they are generally amplified by a factor of 1 by alpha. While the low frequency control signals, they undergo unit amplification, because at low frequency the magnitude plot is 0 dB. So 0 dB is nothing but, so 0 dB is equivalent to unity gain, right? So if k is equals to 1, so 20 log k will be equals to 0 dB. right? So the control signals which are there, that is not getting amplified, but the noise signals are getting amplified. So obviously will not, so you can say that the signal to noise ratio at the output is not very good. So it is poorer with respect to, compared to the input. Okay, so that is why what we do is that we try to keep the value of alpha, generally we try to keep the value of alpha not less than 0.07. Commonly it is generally used as 0.1. Now let's talk about the lag compensator. Okay, so lag compensator, it also basically it has one pole and one zero, but here in this case the pole is located closer to the j omega, closer to the origin. So in the previous case the zero was located closer to the origin and the pole was located farther away, but in this case it is just the other way round. So in a similar way, you can write the transfer function of the of this lag compensator. So GCS will be given by tau s plus 1 divided by beta tau s plus 1, and this value of beta is given by ZC by PC, and obviously this 0 by this pole, so magnitude of the 0 divided by the magnitude of the pole will obviously be greater than 1, right? So in this case, what you can, so in this case, if you, so this is the electrical realization of the system, right? So you have this R2 and C here, and across this R2 and C we are taking the output. So if you simply find out what will be the transfer function of the system, so E0 by EI, so E0 by EI will be equals to R2 into 1 by SC. You can simply rearrange the terms and you will end up with an equation which looks like this. So from this equation, if you substitute the value, let's say if you consider tau is equals to R2 into C and beta is equals to R1 plus R2 by 2. So that means beta is obviously greater than 1. Okay, so then the transfer function, it can be expressed in this form. So 1 by beta into 1. So you have 1, so this is beta, so 1 by beta multiplied by S plus 1 by, this is tau. So S plus 1 by, this is beta and this is tau. So there is, yes, S plus 1 by beta tau, right? So this is the realization in the electrical domain, and in the electronic domain we have already seen that the same whatever was the configuration using the op-amp, you just have to change the values of R1, C1 and R2 and C2 in order to shuffle between a lead compensator and a lag compensator. Now, if you draw the polar plot of this lag compensator, if the transfer function is given by 1 by beta by this, so the polar plot will look something like this. Okay, and similarly, if you draw the Bode plot for this transfer function, the Bode plot will be, so here also you have two corner frequencies. So one corner frequency is at 1 by tau and the other one is at 1 by beta tau, right? And since beta is greater than 1, so obviously beta tau is greater than tau. So you can write 1 by beta tau will be less than 1 by tau, right? So that means this corner frequency will come earlier than 1 by tau. So simply drawing the Bode plot, so at the corner frequency omega equals to 1 by beta tau, you have, till that point there was 0 dB line, and this point there is a pole, so that means you will have a minus 20 dB per decade. Till this 1 by tau, at 1 by tau you have a 0, so that means the contribution of this 0 will be plus 20 dB per decade. So previously it was minus 20 dB per decade, now an addition of plus 20 dB per decade has been done, so that means overall the slope it gets cancelled out and you will end up with a 0 slope. Okay, so that means a horizontal or a straight horizontal line. So this is the Bode plot for the lag compensator. So here in this Bode plot you see that the high frequency signals, that is the noise signals which were of high frequencies, the amplification of these noise signals, that is much, so this is, you can say this is basically attenuated. Since this is in the negative, so this is minus 20 is there, so minus 20 of sorry, log beta is there, so that means that the high frequency noise signals that are attenuated if we use a lag compensator, and at low frequencies, that is the control signals, that will again also have the same amplification of 1. So what you can do is that you can realize this GC by, so if you have this network, so this network, so if you compare this network. So this is, you have 1 by beta multiplied by this term. So this will be, so in order to realize this, if you simply have a multiplicative factor of 1 by beta to this, then this GCS and this GCS will become same, right? So that means we can say that the GC can be realized by the previous network